charges, plus 2 by 3, minus 1 by 3, or 0 and minus 1, as we go down into the each generation. What the generations are organized by the increasing mass. All the visible matter in the universe is made from the first generation of particles. That means your up quarks, your down quarks, and your electrons. This is because all the second and third generation of particles are unstable and they quickly decay into the stable first generation particles. Then spin, we can we have a property of particle which we call spin, and spin basically is a value of angular momentum assigned to all the particles. That means when a top spins, it has certain amount of angular momentum. The faster it spins, the greater the angular momentum. So this idea of angular momentum is also applied to the particles. What it appeared to be an intrinsic, means unchangeable property. For example, we can say that electron has and will always have half spin. So we cannot say that electrons are changing spin. They are unchangeable. In quantum theories also we can say that the angular momentum is measured in terms of units, that is h crosses, you know the h by 2. Then we classify these particles according to the spin also. And the particles which have spin half, we call those particles, or we characterize those particles as fermions, whereas the particles which have spin 1, we characterize those particles as bosons, and the particles that spin 0, we call them as stable particles. So most of the matter we see around us is made of protons and neutrons. And these protons and neutrons, they are not fundamental. They are further made up of quarks. And these protons and neutrons, they are composed of up and down quarks. So there are 6 types of quarks. And this is 3 pairs: up down, downstream, and top bottom. Bottom of beauty, you can say. So quarks have the unusual characteristic of having a fractional electric charge, unlike your protons and electrons, which have integer charges, either plus 1 or minus 1, you can say. Then quarks also carry another type of charge, which is called color charge, which we will discuss now. Then the quantum numbers. Here I have a table of quarks with their charge and with their spin. So you can see from this slide that up quark has charge plus 2 by 3, whereas all these quarks have spin half, means they are fermions. And then your down quark has spin minus 1 by 3, strange has spin minus 1 by 3, charm has spin plus 2 by 3, and so on. Then fractional charges also. So Murray, Gell-Mann, and Lewis proposed the idea of quarks to find some of the order in chaos of particles. It means we have baryons. Baryons are those particles which consist of 3 quarks, Q, Q, Q. And mesons are the particles consisting of quark and quark, Q, Q, Q. So on the left hand side in your slide you have baryons, Q, Q, Q. You have all the baryons, and these are the particles. On the right of this table you have delta plus plus, and the constituent of delta plus plus. The baryons, 3 baryons, you have delta plus plus, then delta plus has 2 up and 1 down quark. Delta 0 have 1 up and 2 down quark, and like that. And on the right hand side you can see the meson Q bar, where 50 has quark U bar, 5 plus has quark U D bar, and so on. You can see from the table the quark contents of each particle, baryons as well as their mesons. Then the problem arose with some of the introducing quarks. the fractional charge even seen before, then the quarks are not observable. Not all quark combinations exist also in nature. Then also there is some difficulty that it violates the Pauli's exclusion principle. That two particles, they are made of same quark content. From here you can see that delta plus plus is made of three up quarks, and this violates your Pauli's exclusion principle also. So for that, so we have another property of this, that is color charge. Means so we have to explain why not only those combination of quarks and antiquarks that have integer charge, and why not one arrow charge q or 3q or 2q and 1q bar. So in this situation you can say that q doesn't exist as such, q doesn't exist, what 2q bar exists as we learn, 2q and 1q bar not doesn't form what q, that is your variance, quark. So you can see from here, so Gell-Mann and others then thought that the answer has to lie in the nature of force between the quarks. And this force, so is called strong force. And the new charge is that using this force, strong force, is called color charge, even though they have nothing to do with your ordinary. So they propose that quarks can have three color charges, and this type of charge was called color because certain combinations of quark colors would be neutral, in the sense that three ordinary colors can give a white neutral color. So only particles that are color neutral can exist, which is why only
रेकॉर्डिंग कशाला करायची
q bar C.
घरी जाऊन ऐकायचं तुम्ही डबल डबल कुठं नाही करायचं.
So here we come to that
काय समोर लिहून द्यायची असते का शेवटी
we have studied that we have
आणि त्या पॉईंटवरनं शोधून लिहायची समोर काय काय मुद्दे होते काय
then we have also the antiparticles, then the quarks have fractional electric charges, and then we have also studied still now a new charge of quarks that has been introduced, and this charge is called color charge. Then we have forces also. Although they are and they are all based on your force fundamentals. That means we know the four fundamentals. That is your gravity, your weak force, and your strong force. But the strong and weak forces only act at a very short distances, and they are basically responsible for holding together. The electromagnetic force acts between the two charges, but the gravitational force acts between the mass. So the force is responsible for the tendency of atoms not to overlap each other, and thus we can say this is responsible for the stiffness or the thickness of the matter. But it also depends on the electromagnetic force that binds your constituents of every atom. So these forces, all other forces are based on these forces. For example, if we talk of friction, friction is an anticipation of the force acting between the atoms of two surfaces. Or we can talk of the forces in Spring's model by Hooke's law, which is also the result of your electromagnetic force. Or you can say the centrifugal force, which are the acceleration forces which arise, they are arising from, you can say, the acceleration of the Alright. What the four fundamental forces, the forces at the fundamental level are the particle means here quarks and leptons, because they are the building blocks of all the other particles. They interact through different forces, which we understand as due to the exchange exchange of field quanta, it is known as your gauge photon. So first I will talk about this electromagnetic force. So electromagnetic force, your carrier is exchange carrier is your photon. Whereas if you talk of one force, photon is the carrier. Whereas in weak interaction we have W plus minus and Z0 boson. And in gravitational interaction we have particles of which we always ignore the gravitation. We only talk about electromagnetic and weak force. The standard model, which is the basic model of particle physics, it tells us to describe the interaction of quarks and leptons via the gauge photon. There is also postulated but not yet declared a state of that means state of this particle is zero. So what is the difference between now I will tell you here what is the difference between a force and an interaction? What is the difference? This is a very speaking force. What is force? Force is the effect on a particle due to the presence of other particles. And the interaction of a particle includes all the forces that also includes the phase and that the particle might go through. The reason this gets
स्पीकरचा
that
उपयोग झाला
we know that most of the people even
ते कानात घालून बसा
usually use force and interaction interchangeably, although interaction is more correct as compared to if we talk about force.
हे
For instance, if we call
पांढरसला additional मिळालं म्हणून
carry the interaction force carrier,
ऑनलाईन मागून दिला पण 600
say that the term interchangeability, what you should here say that
इलेक्ट्रॉनिक्स दुकानावरच नाही म्हणजे
in a
बरोबर
concept
का काय सांगता येत नाही मला
you can
ते दुकान पडून पडून असं खूप दिवस पण
see
घेतलं
the
सर
forces.
असं होऊ शकते
Think about the forces and
इलेक्ट्रॉनिक्सचं कसं
analogous to the following situation. Here I have just give
दुकानावर कसं ते
gave
काम
here
करतं.
some
म्हणले त्यांनी तिची MRP 700 आहे म्हणजे
the board. One person moves your arm and is pushed back. A moment later, other person grabs and the object and is driven back. Even though we can't see the basketball, but we can assume that one person threw a basketball to another person without you to see his effect on the people. That means it turns out that all the interactions matter particles are
चेक
change of force level. Different type of particle are there. And these particles are like the particles of between the matter particles. Then here I will give an example. You can see attractive forces means they are generally take you can say granted that an object present can just effect another object
तर इलेक्ट्रॉनिक्स ते खूप खोच्या राहते
you can say how can two
लय
objects
भारी
affect one another without touching.
बरोबर लागते ते प्राईस
So that
बघा आम्ही तयारी टाकलेला मच्छरला
suppose here that the invisible force
कॅट आहे बा इकडे कॅट आहे
change of force
तिकीट
level.
आहे
So the particle physics has shown that we can explain the force of one particle acting on another to an incredible precision by the exchange of the force carrier. So one important thing you can see here, or you know about the force carrier is that particular force carrier particle can only be absorbed or produced by the metal particle which is affected by that particular force. For instance, electrons and protons have electric charge. So we can produce and absorb the electromagnetic force. Is then these forces have some range also. The range of forces is related to the mass of exchange of particles. So an amount of energy, you can say here I have given the equation del E is equal to mc square. So delta T is the Born balance of the principle. That is delta of E is equal to E is approximately the maximum distance the particle can travel. That is your balance, is your curve to delta T. So there is some overlap of equations. So, which forces act on the weak particles? Where you can see. The weak force acts on between all quarks and leptons. So, all the quarks and leptons, they feel the weak force. The electromagnetic force acts between all the quark particles, and the strong force acts between all your quarks. No lepton is there in strong force, only quarks. Whereas in weak force, you have quarks as well as you have leptons. And the gravity, we don't take or consider gravity in your particle. Just okay. What about the nucleus? We have another problem with atoms. So, what binds the nucleus together? The nucleus, you can say, the nucleus of an atom consists of bunch of protons, as you know, protons and neutrons, then they are crammed together. So since the neutrons have no charge and the positively charged protons repel one another, why doesn't the nucleus blow apart then? We can't account for the nucleus staying together with just electromagnetic force. What else could be there? Only electromagnetic force can't put this nucleus together. So there is strong interactions to understand what is happening inside the nucleus. We need to understand more about quarks that make up the protons and neutrons in the nucleus. So you know that protons and neutrons, they are bearing, they are made up of the three quarks. So quarks have electromagnetic charge, and they also have an altogether different kind of charge which we talked earlier, that is your color charge. So the force between color charged particles is your strong force. So the force is primitively called strong because of color charges, and the strong force holds these quarks together within your protons and neutrons are, and its carrier particles are gluons because they tightly glue the quarks together. Gluons, they tightly glue your quarks. Your proton is made of three quarks, and the gluons, they tightly glue these quarks together within your proton or within your neutrons. Then the color charge. Color charge behaves differently than your electromagnetic charge. And gluons themselves have color charge, which is wired not at all like your photons, which do not have electromagnetic charge, while the quarks have color charge, composite particles, and they are made out of quarks, and they have no net color charge. So for this reason, you can say the strong force only take place on the really small level of your quark interaction. So the color charge, in color charge we can say that we have three color charges and three corresponding anti-color charges. And each quark has one of three color charges, and each antiquark has one of three anti-color these charges. Just as a mix of your red, green, and blue light, you can yield a white light. So, in the baryon combination of your red, green, and blue quarks. So then gluon emission and absorption always changes the color. And in addition, you can say color is a conserved quantity. And the gluons can be thought of as carrying a color and an anti-color. And there are 8 gluons, 9 gluons are there, but one is neutral, and you can say so this is the color. When two quarks, you can say, are close together, this is the diagram. Two quarks are close to one another and they exchange gluons and create a very strong color force that binds these quarks together. And the force field gets stronger as the quarks get further apart. So the quarks, you can say, constantly change their color charges as they exchange the gluons within your quarks. So quark confinement is also a phenomenon. So you can say is the phenomena that color charged particles like your quarks cannot be isolated. That means quarks are confined with other quarks by the strong interaction to form pairs or triplets. So the net color charge is your neutral. The force between these quarks increases as the distance between them increases. So no quarks can be formed individually. So this is just like your magnet. If you try to cut a magnet, it has a north and south pole. So similarly, when we move apart a quark from one another, a quark antiquark pair is produced. So, however, as the two quarks separate, the gluon field form a narrow tubes or strings, you can say, which are quite different from your electromagnetic forces, that is charge. Because of this behavior, the color force experienced by the quarks in the direction to hold them together remains constant. So here in this figure you can see that when two quarks become separated, as happens in the accelerator collision, at some point it is more energetically favorable for a new quark antiquark pair to pop up out of this vacuum. So in so doing, you can say the energy is conserved because of the energy of the color force field is converted into your mass of the new quarks, and the color force field can relax back to an unstretched, you can see from this snap. You have then residual strong force. So the strong force, as we know, that binds your quarks together because quarks have color charge, but that still doesn't explain what holds the nucleus together. Since positive protons repel each other with electromagnetic force and the protons and neutrons are color neutral. So the answer is that, in short, we can say that they do not call it the strong force for nothing. Strong force between the quarks in one proton and the quarks in another proton is strong enough to overwhelm the repulsive electromagnetic force. And this is called the residual strong force, and it is what glues your nucleus. Then the second is your weak interactions. So there are 6 kinds of quarks and 6 kinds of leptons. What all the stable matter of the universe appears to be made of just the 2 least massive quarks, that is your up quark and down quark, and the least massive charged leptons, that is your electron and your neutrino. So it is the only interaction which is capable of changing the flavor. Weak interaction is the only interaction which is capable of changing the flavor. So it is mediated And the weak interaction is mediated by heavy gauge bosons, your W plus minus and Z0. So due to the large mass of weak interaction carrier particles, their mean life is limited to your 3 into 10 raised power minus 25 seconds by your uncertainty principle. And this effectively limits the range of your weak interaction to 10 raised power minus 18 meter. That is 1000 times smaller than the diameter of your atomic nucleus. And it is the only force which affecting your neutrinos. Weak force is the only force which affecting the neutrinos. Since the weak force is very, you can say, weak force is a short range force, and it is most noticeable effect is due to its other unique features, that is your flavor changing. So consider a neutron. We know that neutron is made of three quarks, one up quark and two down quark, and famous beta decay reaction where neutron decays into proton, electron, and anti-neutrino. So neither electromagnetic nor strong interactions allow the change of flavor. What only the weak interactions we can say the flavor is changing. This effect is also noticed only in your weak interaction, the flavor changing effect. Gravity, we will not talk about gravity in the particle physics. Then we have the most general or striking properties of elementary particle is the tendency to disintegrate. That means universal principles. Every particle decays into lighter particles unless prevented from doing so by some conservation laws. Obvious, we have some conservation laws which we study in particle physics. That is the momentum conservation. Momentum should be conserved when some decay is there. The momentum should be conserved. Only then the decay is possible. Then the energy should be conserved. The charge should be conserved. Then we have stable particles also like your neutrinos, your photons, your electrons and protons. So neutrinos and photons, we know that they are massless. There is nothing to decay for them into other particles. Still, photon, we can say that photon decays into E plus E minus and so on. The electron is the lightest of all the charged particles, and their conservation of charge prevents its decay. Then we have some other conservation laws that baryon number should be conserved. Then you have lepton number should be conserved in an interaction when there is some decay is there. Then strangeness should also be conserved. Charm should also be conserved. Then what governs the particle decay? So each unstable particle has a characteristic mean lifetime, tau, which is related to half lifetime by the formula. This is the formula. For muon, as we know that the muon, its lifetime is 2 into 2.2 into 10 raised by minus 8 second. For pion, it is 2.6 into 10 raised by minus 8 second. And for neutral pions, phi 0 it is 8.3 into 10 to the minus 70%. Most of the particles exhibit several different decay modes. Most of the particles, they decay in with different reactions. For example, kaon. Kaon decays into muons and neutrino muons. And the probability of their decay is 63.4%. Kaon also decay into pi plus, means positive pions and your neutral pions, and the probability of their decay is 21%. Then these kaons also decay into pi plus and pi minus. Two pi plus and one pi minus. and the probability of their decay is 5.6%. So this probability of decay is called branching ratio. These are called branching ratio. Then we have the decay is governed by one of the three fundamental forces also, the strong force, the electromagnetic force, and your weak force. Like in the first reaction, delta plus plus decays into, you can say, proton plus pi plus, but this is due to strong force. Electromagnetic, this pi zero decays into two photons, and this interaction is basically due to your electromagnetic force. Then your sigma, it decays into neutron plus electron plus anti-neutrino, and this decay is due to weak. Because whenever in an interaction you find some neutrino is there, then that reaction is your weak reaction. That reaction is due to, you can say, weak, a weak force. So the branching fraction for a decay is the fraction of particles. I will skip this. Then you have momentum energy conservation law also, which is every decay followed that energy should be conserved, momentum should be conserved in a reaction. So like here you can see this lambda zero, this is a baryon, consists of three quarks, U, D, and S, and it decays into your pi minus pi plus pi plus, and this reaction is allowed. So why you can see from here that the mass of your lambda is 1116 MeV, mass of proton 938 MeV, mass of ion is 140 MeV. So your mass of lambda is always greater than mass of your proton plus mass of your ion. So from here you can see that mass of lambda is your 1116, and the difference is 38, so this reaction is allowed. So then in particle physics we use Feynman diagrams also. So Feynman diagrams are basically the graphical ways to represent the exchange of forces. So each point at which line comes together is called the vertex, and each vertex one may examine the conservation law which governs the particle interaction, and each vertex must conserve charge, baryon number, your lepton number, and other conservation laws also. So these Feynman diagrams are developed basically by Feynman to describe the interactions in quantum electrodynamics, QED. And the diagrams have found use in describing a variety of particle interactions. They are space-time diagrams also that you can see from here. You can see from this diagram that particles are represented by the lines with arrows to denote the direction of the interval, with antiparticles, arrows reversed. Virtual particles are represented by a wavy. Whenever we have a virtual particle, we can represent it with wavy or broken lines and have no arrows. So all the electromagnetic interactions can be described with a combination of some primitive diagrams like this. So here you can see clearly that only the lines entering or leaving the diagram represent the observables. So here the two electrons enter, exchange a photon, and then exit in the upper one. Then the time and space axes are usually not indicated. Then the vertical direction indicates the progress of time upward, and the horizontal spacing does not give the distance between the particles. But after being introduced the electromagnetic processes, Feynman diagrams were developed for weak as well as strong interactions also. So here you can see the different Feynman diagrams for different forces. The first one is for electromagnetic. So you can see that virtual photon is mediated. In the second, you can see the weak force. Your W minus boson is mediated, and downward on the left you can see some quarks, and the color charge is there, and you can see from here two protons, then pions exchange with nucleons or strong force. Then here you can also see the decay of your lambda 0 to pion plus pi minus. So this is basically a strong decay, and it occurs due to the emission of gluons by one of your d quarks, one of your down quarks in lambda 0 baryons. You can see from this figure, the emitted gluon does not change the flavor of the quark. So we still have a d quark in the final state, and then this gluon is split into two quarks, U and U bar. So the U quark combines with the initial U and D quark in lambda 0, and this leads to arising a proton. You can see from here. So this is another Feynman diagram. Here this is a weak force is here in pi plus, and pi plus becomes mu plus muon. So you have neutrino here, neutrino is here. So if neutrino is here, you can see that this is a weak interaction. So one of the quarks change its flavor. So this is the property of weak interaction, that we can change the flavor. So here you can see the flavor is changed. This is the main feature of your weak interaction.
तो अभी पापा लेके आएंगे अंकल को ठीक है.
In both the cases we have virtual double boson, and they arise for a very short time. From here you can see sigma 0 which decays into lambda 0 plus gamma. So here, so it is also not a standard pattern. It does not involve any exchange of gluon. So this is a radiative decay, or this is caused by your electromagnetic force.
They also break continue.
So some of the decays which are allowed. So I am giving here the examples of these decays are allowed. The sigma 0 which decays into lambda plus pi 0. From here you can see that sigma minus indicates into 1 plus pi minus, then cascade 0 indicates into pi minus plus and cascade minus pi minus plus lambda, then you have electron plus pi. Then parity is also some of the properties which we study in particle physics. So what is the parity? So this is one of the conservation laws which applies to particle physics of parity. So quarks, we can say, have an intrinsic parity, which is defined to be plus 1, and an anti-quark has parity minus 1. So the neutrons are defined to have an intrinsic parity. Parity means the mirror reflection. If we have X, Y, Z, by transformation, we can see it is minus or mirror reflection. Non-conservation of parity. So electromagnetic and strong interactions are invariant for the parity problem. That's what parity is. Conserved. Parity is conserved for electromagnetic the product of your parity and your charge conjugate. These are the two species. P for charge conjugate and which transform a particle into antiparticle, and P is the parity which creates another image of the system. So the parity symmetry is also violated in the weak interaction. See, CP, we can say that CP is violated in the weak interaction. Strong and electromagnetic interaction which need to be invariant under your combined CP transformation. What is CP? You can say is slightly violated during certain phase of the study in weak interaction. When you switch off all your
Dr. Kaushal, please turn off your mic.
Sir, please turn off your mic.
Dr. Kaushal, please turn off your mic. सर आप प्लीज कंटिन्यू करिए मैं इनको कॉल करता हूँ
हाँ ठीक है ओके then other is your CPT. Many of the profound ideas in nature manifest themselves as neutral and existing in a physical experiment suggest that something is conserved or remains. So many of the questions usually but not always hold those charge constellations, your parity and your time. Charge constellation that is reversing the electric all your
Refresh.
parity.
संशोधन आहे
नवीन संशोधन आहे
आपलं वायफाय कावर चाललं ना वायफाय म्हणजे नाही चालू आहे आता बंद झालं एवढ्यात
So the evidence for quarks. So the basic idea is that here one fired upon the proton charge, the cloud is there. And in the downwards figure, one contains a current charge. Some of the time, just you can see that
coordinate
two electrons are deviated. Then look at this figure also. You have protons using electron microscope, so the resolution dependent on your wavelength and what is happening in your electron proton fluid. You can see from here. One electron is there, one proton is there, proton is radiated, then you have electron is produced and one of the photon. From here you can see one quark is there, D, and two quarks, U, and D is produced. From here you can see in the figure. From here also you can see the strength of the force between the color charges which increases with the separation also. But you can never see the free quarks in this figure. So this I will skip. Then this is one of the experimental results of the event from which was taken from the Opal experiment at lab. You can see the collider experiment, E plus E minus is there, Z0 means this is a weak force, and two muons, mu plus mu minus is produced. You can see from here. So this is another event from this experiment. What here you can see that a photon has been emitted by one of the muons. So photon is emitted from one of the muons, you can see from this figure. Then here you can also see that Z boson may also decay to a pair of quarks, Q bar. And as the quarks apart, the energy in the field between them is passed by the color charge builds up and further quarks and antiquarks are formed. So these are all the experimental results conducted at LabX, Opal experiment at lab. So this is also the same. Gluon is exchanged in this. You can see from the figure. So then cross section. Cross section is another important parameter which we study in the particle physics. These, what is cross section? The strength of a particular interaction between two particles is specified by the interaction cross section. So the strength of the particular interaction, that means when we have a projectile, when we have a target, then first we will find out the cross section. That means what is the probability of that projectile to hit that target? What is the probability that the projectile hits the target? That we calculate. So you can see from here the cross section is crucially key that opens the communication between the real world of the experiment and the abstract. That you can see. Cross section is basically the probability which I told you. We can measure the probability that two particles will interact in experiments. We can also calculate this cross section in a model. That means in simulations also we can calculate the cross section fields. That will incorporate our understanding of the forces acting on the subatomic particles. And I just give an example. If suppose we have a proton and that we have a target, so what is the probability of that proton to hit a target? And one experiment is this, and another I take my projectile is neutrino, and then I have some target. Then what is the probability of neutrino to hit that target? So from these two experiments, I'm just giving an example. From these two experiments, so the probability of proton to hit the target is more as compared to probability of neutrino to hit the target. Why? Because the mass of proton is more as compared to the mass of your neutrino. So this is basically the cross section which tells us about the strength of a particular interaction. How much probability that that particular projectile has to hit that target. Then so this is another experiment at SLAC, Brookhaven. So here the accelerator has E plus E minus, a collider experiment, and the ratio is given by taking the cross section E plus E minus to QQ bar by the cross section of mu plus mu minus. So as from here you can see the R should be 2 for low energy, where we have U, D and S quarks, and R should be this. So from here we can see that we can find out this ratio of cross section when E plus E minus gives us quark mesons, that QQ1 means mesons, and E plus E minus gives us leptons. So this is basically the ratio of cross section of quarks and divided by the cross section of your muons. So then we have the results from this. So this I will skip. This I will skip. Then this is also one of the experimental results where we have produced a new particle that is your Jepsi particle. So Jepsi is also a particle which is produced from your collider experiment, E plus E minus experiment. So for this, two different independent experiments gave the same results. And Jeff's size basically also consists of CC bar, one quark and one antiquark. The constitution or composition of Jeff's size consists of two quarks, QQ bar. Basically, this is the meson QQ bar. And these are the experimental results for this. Then you have the mass of jet size. The mass of jet size is your 3097 and lifetime is your 10 to the minus 20 seconds. And the branching ratio, this is also important, branching ratio. The jet size decays into hadrons, 88% probability of jet size which decays into hadrons, 6% of jet size probability which decays into E plus E minus, and 6% probability of jet side decays into U plus minus. So I will skip this details of, then we have some, so I will skip this Charmonian states, I will just skip this. Then this is also one of the examples of charm particles. We have B plus mesons which decays into your K naught electron and antineutrino. Then we have lambda which decays into proton and K0 bar. Then sigma baryon which decays into lambda 5 plus K. So I think I should stop here. So any question related to this?